Last lecture, we've considered a program, an idea of specifying some considerations concerning Poincare duality for singular spaces, and the idea was as follows. One attempts to associate to a stratified pseudomanifold a space which we call an intersection space, depending on a perversity P. And this should be done in such a manner that if you look at the ordinary homology of this space, and I will always assume real coefficients, and we abbreviate this by HI star P of X, that these groups satisfy Poincare duality between complementary degrees and complementary perversities as usual. And so that is the idea. Now I've shown you last time how one can construct these spaces for a space with isolated singularities. If the singularities of X are not isolated, attempt a process of fiber-wise Moore approximation. And at this point, things get very interesting. So there is now not a close parallel anymore between the development of intersection homology, because at this point, either of two things can happen. Either such a fiber-wise Moore approximation is possible or it is not. So in general, it is obstructed. And we know some obstructions by now for this to be possible. This is connected also to the so-called equivariant Moore space problem of Steenrod, an old problem from the 1960s. And things like that. So the problem is that Moore approximations are, contrary to Postnikov sections, Postnikov approximations, not entirely functorial and cannot be made so. And therefore, you cannot always literally form a bundle out of a given link bundle, form a bundle of Moore approximations. And however, whenever this is possible, you get an intersection space. So that is the general philosophy. And there are many cases known where one can do this, but there are certainly also cases known where the obstructions do not vanish. So implicitly then, this process also singles out implicitly a class of stratified pseudomanifolds for which such spaces exist. And this goes both ways. If you can form the space, you can draw conclusions about the topology of X and vice versa. So there's a very interesting tension then between all these concepts and structures. So unfortunately, I cannot go more deeply into this. But what I want to mention is, again, for isolated singularities, so let's return to that case, for isolated singularities. So let's assume there's just one. So that's sort of the most basic case. So there is a compact manifold M oriented, and along the boundary we attach the cone. The boundary is then also the link of the singularity. For such a manifold, we have, at least in the problem session, considered what the intersection homology looks like. So it is worthwhile comparing that computation with what one would get for the HI homology for such a space. And what happens is the following. First of all, there was a cutoff dimension involved. If you remember, we said last time that we would take k to be n minus 1 minus pk. N is the dimension of X. And then depending on that cutoff, the answer is the following. These groups hi in degree I with perversity p of x can be computed like this. If I is large, if it's above the cutoff, then you get the absolute homology of M, and if it's below K, you get the relative homology. And here maybe I want reduced to be entirely precise.
There's a typographical mistake. It's case n minus 1 minus p of n.
Yes, yeah, this must be an n, of course. Thanks. So notice it's reversed. If you remember what the result that we had earlier this week for intersection homology, the absolute homology was in low degrees and the relative in high degrees. And now one can show that it gets reversed, but perhaps that's perhaps not so interesting, but what's really interesting is what happens in the cutoff degree itself. So what happens when I is equal to K? And in that case, you have the following T-shaped diagram of two exact sequences. Let's look at the kth homology of M. And in there is the kernel of a certain map. And the map is the canonical map induced by the inclusion from the absolute homology to the relative one. And so the quotient is, and this we know already, is intersection homology. We've computed this earlier in the course. So this is intersection homology. So it's a quotient of the absolute homology. But then this is itself contained, the absolute homology of M is itself contained in hi of x. I'm sorry, this should have been an x. And the term that's missing, however, to make up hi of x in that degree k is the image of a map, and it's the connecting homomorphism from the relative homology mrel L to hk minus 1 of the link. And so this sequence gives you now, on the one hand, a complete way of calculating this for an isolated singularity, but it also displays the relationship that these new groups have with their classical intersection homology groups. This also shows, if you think about it, that the rank of HIK is always at least as large as the maximum of the rank of the absolute homology and the relative homology, whereas, after all, the rank of the intersection homology in the cutoff degree is smaller than or equal the minimum of the rank of the absolute homology and the rank of the relative one. So the upshot is therefore that in that particular degree k, this group is typically much larger than the intersection homology group. And we have seen this in my last lecture for the example of the pinch torus, where the intersection homology in the middle degree, which was 1 for the pinch torus, was just 0, whereas the rank was 2 for the HI homology in degree 1. Right? So that's already, that exemplifies this general picture. Okay. Now I want to do another example, a key example, which displays many interesting features here. In particular, it displays some stability properties under deformation of singularities, but it also displays relations to mirror symmetry and relations to physics. So I want to discuss a key example in some more detail, a non-trivial example. And that's the example of a Calabi-Yau quintic. So that's the following projective variety. So in fact, I'll define xs, and so s will be a complex parameter which is close to 0. And the variety that I want to look at is z0 to the 5th plus and so on, z4 to the 5th minus 5 times 1 plus s. So here's the parameter, z0 times and so on times z4. So this is in CP4. So that's the projective hypersurface that I want to look at in CP4. So we notice the following about this. Well, what if s is not 0? If this parameter s is not 0, then a quick calculation shows you that this variety xs is non-singular. Right? So this is a nice manifold, and in fact it's a Calabi-Yau manifold. So it's non-singular. However, when s approaches 0 and then finally becomes 0, this variety x0, which I'll also sometimes simply write as x, that's now the singular variety. This x0 then becomes singular, is singular. And in fact, again, a calculation shows that it has precisely 125 isolated singular points. And for the algebraic geometers among you, these are so-called nodes. These are all so-called nodes. So there are a lot of singular points now all of a sudden developing, and a lot of cycles collapsing in the space as this S becomes 0. So I want to, for this deformation, compute all of the well, maybe I won't compute it, at least I'll show you the results of a computation of all these homology theories that we've discussed here for this example. And then we'll discuss this table a little bit. So I want to make a table over here where we want to first look at the homology and the rank, the Betti numbers, of the homology, the ordinary homology of xs. And here s is not 0, so for the non-singular guy. And then I let s be 0. And then we have various theories that we could look at. First of all, we could, of course, look at ordinary homology for the singular space. We can then look at the intersection homology, x0. And as I say, if I don't write a perversity, I always mean the middle. And there's no question here about which middle I should take, the lower or the upper one, because this is a complex variety of real dimension 6. The isolated points of even codimension, and there the lower middle and the upper middle perversity are equal. Therefore, it doesn't make a difference, right, which one I take. So that's that group. It's well defined. And then I also want to look at hi, also with the middle perversity of x0. Okay, so let's look at those. So the interesting degrees, of course, are 2, 3, and 4.
What is the first homology referring to?
Well, it's 0. These are simply connected, and so it's not very interesting.
Oh, you mean if S not equal to, this is S not equal to 0?
Here it's not 0, and here it's 0. In all these columns, it's 0. So what happens here, so one can calculate that you get 1, 204, and 1. So there's a huge number of middle dimensional cycles, for example. And you also see that, as expected, Poincaré duality holds, of course, because this is this is a manifold. Right? But when it becomes singular, then you get, as it turns out, you get 1, you get 103, and you get 25. So the first thing you notice is that, of course, Poincaré duality is destroyed, which is not unexpected. So it's better to look at one of those theories, right? This does not have Poincare duality anymore. By the way, you should think of this 103 for some reason as 2 plus 101. Now, if you compute intersection homology, you get here, in fact, what happens is you get 25, 2, and 25. So, for example, if you compare it to these two columns, a huge number of cycles is lost in the middle dimensional homology of intersection homology, which is sort of what I indicated over there. Lots of things will vanish over here, and this is in general much bigger. On the other hand, that phenomenon holds only in the middle dimension. You see that in dimension 2, you have here 25 as opposed to 1 here, right? So lots of cycles are added, if you will, by intersection homology in that degree. And for some reason, you should think of this 25 as, by the way, 1 plus 24. I shall return to this momentarily. It looks a little bit cryptic now, but and for the last column, when you do the calculation, you find 1, 204, and 1. So several things can be observed about this. First of all, notice that both of these columns, as has to be the case, have Poincare duality again. They are nicely symmetric here. But perhaps the most intriguing phenomenon that you see happening here is that this column is exactly the same as this one. And this is, of course, very striking, right? It's sort of hard to believe that this is just a coincidence, right? It's hard to believe that this is a coincidence, this equality. And again here, it's good to think of this as 2 plus 101 plus 101. The 2 plus 101 you see over here already, and then another 101 are added here by this theory. But as I say, I'll come to this, I'll return to this later. So this is what comes out in this example. So if you also think about the example of the pinched torus, this kind of stability under nearby smooth deformation was also true for the deformation of this elliptic curve, right? Where you get then at x0 the pinched torus, because you had rank 2 and you had rank 2 in the middle. So maybe it's not entirely a coincidence. And in fact, one has the following theorem, which we proved together with Laurentiu Maxim. Let xn be, and you should think of this x as the x0, be a complex n-dimensional projective hypersurface with an isolated singularity, and let xs be a nearby smooth deformation, as in all these examples that we've discussed. Then you can in general say the following. So if you look at the homology in degree I of the smooth guy, and maybe I want reduced again here, then this is given by hi with the middle perversity of x which is x0, certainly if I is not the middle, but n, by the way, I want to emphasize n here is the complex dimension, complex n-dimensional, so the real dimension is 2n, so n is the middle dimension of the space. Right? So you get this. And so in almost all degrees, except for the middle and except for the top, in the top you cannot expect it, of course, because what we said over here is in the top it's always the absolute homology, and so this is always 0. The top homology of a manifold with boundary is 0. So therefore you cannot expect this to be the same. That would be completely unreasonable. But so it's true in all degrees except in the middle, and in the middle, so maybe I'll say it like this. So these are equal, and for I equal n, there is a condition. So Hn xs is isomorphic to Hin of x if and only if the monodromy operator on the middle cohomology of the Milnor fiber of the singularity is trivial. So, so this kind of triviality happens in all the previous examples. It's true for the Calabi-Yau quintic, and it's true in this torus picture. But in general, it is, of course, it is, of course, a serious assumption. I mean, for most singularities, actually, it's not trivial. So I cannot really explain what the Milnor fiber is, a theory of Milnor fibrations and so on, but it's a very classical topic. If you have an isolated singular point in algebraic geometry, you can always associate to it a very nice fibration in the neighborhood of that singularity, and a lot is known about this fibration, and you can use these facts to make calculations near the singularity. But unfortunately, lack of time prevents me to go into this. But this explains theoretically these phenomena. So it's not a coincidence, right? So the answer is it's not a coincidence that this is equal. Moreover, if the monodromy operator is not trivial, we have precise estimates how these are related. But again, I can't go into this here. So I wanted to say a few words about relations to physics. So there is in physics, you have what's called a conifold transition. And the example that we've just considered is an example of such a conifold transition. So what you do is the following. You start with a Calabi-Yau manifold, depending on a parameter, xs, just like we did in the example. And then you let s go to 0, and you obtain a singular space, x0. And there is, however, a second step. This always consists of two steps. In the second step, you resolve, and you form a new space y, which will also be, again, a Calabi-Yau manifold. So it is in particular non-singular, but in fact, it's even a Calabi-Yau manifold. And there is a map here. This is a resolution map, but even more, it's what's called a small resolution. So the pre-images that you use to resolve this shouldn't have too high dimension, and too high means 1 here, complex dimension, or real 2. So in other words, what actually happens is that 3 spheres here get collapsed to a point, and the point will then be a singularity, and then you blow up the point by putting in a P1, which topologically is an S2, and you resolve by putting in these P1s, but they have dimensions smaller than dimension 3, and so it's what's called a small resolution. And so this is important in physics, because in physics, recall, the idea is that you say you want to describe the world in terms of a 10-dimensional space, in string theory in particular, which is often thought of as a 4-dimensional space, like Minkowski space, cross x6, where this is the real dimension, or maybe it's also a bundle over M, sometimes it's a bundle over M, sometimes it's a product, where this is a Calabi-Yau manifold. So this is called the target space in string theory. In any case, it's not clear which Calabi-Yau manifold you should take. Therefore, it's important to have a way to go from one Calabi-Yau manifold to another one and see what happens in the course of doing this. And the conifold transition is a nice way to relate different Calabi-Yaus to each other. And in fact, it's believed that more or less such transitions should make it possible to go from any given Calabi-Yau manifold to any other one.
What is the meaning of conifold?
Well, this is the physicist's name for the conical structure, right? I mean, near the singularity, the neighborhood doesn't look like a ball, but like a cone on something. And so they called it a conifold. We would call it a stratified pseudomanifold, right? Or maybe a Whitney stratified space, which in fact it is. I mean, it's given by equations, and so that's. So you can also think of, so what happens in the neighborhood here? So as I said, 3 spheres collapse. So a good picture to draw is this one. So I always like to draw this picture where you imagine that this is S2 and this is S3. And here is an S3 embedded with trivial normal bundle. And so this is a cone here. Here are these cones, and they are, of course, they are balls, right? The cone on S2 is a 3-dimensional ball. And so it's S3 embedded in this manifold as a submanifold. And now what goes on in this transition when S goes to 0, this collapses to a point, so the picture would become something like this. And now this is a singular point, and you can see that the link is S3 cross S2. So this one can show for such nodes here in this situation, topologically, the neighborhood looks like the cone on S2 cross S3. And when you blow up these points again, then you replace them by P2s, by the 2-sphere direction, in other words. And so then I would draw it like this. So here you see the P1s replacing the point. And so this is what locally happens near the points in question that we're interested in, near the singularities. So that's how you should imagine these conifold transitions to look like topologically. Now there is a paradigm in physics which asserts that massless particles in the 4-dimensional reduction, so viewed on M4, should correspond to cohomology classes of the vacuum of X. So granted this, a good theory, a good cohomology theory of X should count all these massless particles correctly. Now, on the other hand, Strominger asserts that in the course of such a conifold transition, there are some two branes associated to the P1s, and there are some three branes associated to the S3s that collapse on the other side of the conifold transition. Now, more precisely, these two branes arise in 2A, in string theory of type 2A, and these three branes arise in type 2 string theory in type 2B string theory. Okay? And their mass is proportional to their volume, and they wrap around these cycles tightly, right? But when these cycles collapse here in the middle, then since this estimate remains stable, as the volume goes to zero, so does the mass, and they become massless. They are still there on this space, these branes, but they are now massless. But according to this paradigm, they should therefore appear as cohomology classes. So this should be seen by any good theory for singular spaces from that point of view. And in fact, the theorem is so intersection homology counts the massless two branes correctly. Here it is not so important what precise mathematical model you take for what a brane is. It's only relevant that you can count them, and that we certainly can. And so the count is correct, counts the massless two branes correctly in type 2A theory. But it doesn't count the three branes correctly. If you do the calculation, the physicists tell you how many three branes there should be, but if you compare, the three branes are not visible in intersection homology. So previously there was no theory available that does the other half of the picture sort of correctly, but this is now done by the theory HI that I have introduced, right? So whereas the theory HI that I've introduced here in these lectures counts the massless three branes correctly in type 2B theory. And now I'll return to my table. And you see now explained these funny numerology that I made earlier in this table, because this number 24, these are the massless two branes. So they are two-dimensional homology cycles, and they are seen correctly by intersection homology, but they are not seen by HI. On the other hand, the 101 that I've told you about are the massless three branes for type 2B theory, and they are seen correctly by HI, but as you can see in this example, not by intersection homology, because there are way too few. Right? And the rest of the classes you see don't come from these D branes. They are other fields. They have other interpretations as other fields on that space. They don't come from Strominger's sort of assertion that I quoted here. Okay? So this is briefly just some explanation of some relations to physics. Furthermore, of course, there are then relations to mirror symmetry that probably I won't be able to get into now for lack of time. But it's not surprising, right? Because mirror symmetry, in fact, arose as through certain symmetries between 2A and 2B, string theory. And that these kinds of considerations, A versus B, gave rise to mirror symmetry. And since we observed these counts for 2A and 2B theory, it's not surprising that, in fact, this will then lead to statements involving mirrors of conifolds and statements, predictions about what the intersection Beatty numbers and the HI Beatty numbers of the mirror should be, etc. But I won't write down the formulas, but it's not surprising that this then says something about mirror symmetry. All right, so maybe that's all I want to say about this theory HI and about intersection spaces. So it's clear that there's a lot to be sorted out still in the future in this picture. Now, but I want to return, we return to intersection homology. Okay? I want to return now to intersection homology. And I promised you earlier in the week that I want to give a different description of intersection homology in terms of sheaf theory. And I want to then further use sheaf theory to prove, for example, to prove the duality theorem. Right? And so let's do this now. Now, I believe that there are many people in the audience who have never seen sheaves before. Is this correct? I think this is, yes, okay. So therefore, I'm supposed to explain a little bit about sheaf theory, right? So I will attempt to give a crash course in sheaf theory. So crash course on sheaf theory. All right. So I start, so X is just a topological space to begin with. Now, what is a pre-sheaf on X? It's a system which assigns to every open subset of X, a group or a vector space or a ring, A of U, and then the pre-sheaf is called A. Right? So let's say these are R vector spaces, because this is what we will actually use then when we do intersection homology theory again. So let's say these are just R vector spaces, these AU. Now this assignment should satisfy the following. First of all, if you have a V contained in U, also open, then there is supposed to be the possibility to restrict. So you have restriction maps, and you can restrict down to smaller open subsets. But of course, there could be another set, even smaller, also open, and then you can restrict further. And then, but on the other hand, you could immediately restrict from U down to W, so you also get this map, and of course you want this composition to be commutative, right? I mean, you want this composition to be this arrow. And also you want, of course, that if V is equal to U, then the restriction should just be the identity. So you can phrase this as a functor, but I don't need that language, right? That's what it is. So now, when is a pre-sheaf a sheaf? So A is a sheaf if the following condition G holds. So G stands for gluing. So we have a gluing condition, and it's the following thing. You have an open subset in X, and you have an open cover of that open subset. So all of this is given. And also you are given elements Si in these vector spaces AUI. But you know something. You know such that when you restrict Si to the intersection of a Ui and a Uj, then it's the same as if you restrict Sj to that intersection. For all ij where this intersection is non-empty, of course. So suppose you know that. Then the condition requires then there exists a unique S in A of U, which when you restrict it to a UI, you get the given SI. That's the condition G. That's a gluing condition, right? A priori, I mean, you want to think of these elements as sections of something, but you don't, but it's not actually true, right? You're just assigning groups to open subsets, and that's it. But if in this sense you can glue elements together, then you call this a sheaf. Gaudemont just left the room. Let's see. So we have the notion of a sheaf, but there's another valuable description of this. This is one way to think of it, but there's another way, a very good way of thinking of this, namely in terms of étale spaces. So a sheaf also has an étale space. Now this is a topological space. I'll often write sheaves and their étale spaces with boldface letters like this. A together with a map, pi, down to the space. And so how do you create this? How do you create this A? Well, you first say the following. Suppose you have a point X and you consider all open neighborhoods U of X and the groups that the pre-sheaf assigns to such an open set, then you can take the co-limit over that entire system of restrictions, right, over all open neighborhoods, and we give this a name and call it A sub X. And this is called the stalk. So it's similar to the fiber of a fiber bundle, but here in sheaf theory it's called the stalk. Right? And so you define A to be the disjoint union over all X in X of these stalks. But now this is just a set, so you need to topologize it. And how do you topologize the étale space? Well, you say if you fix an open subset in X and you also fix an element S in AU, then for any such choice, you consider the set SX in AX for X in U. In other words, what I mean is this. You have the section. Now, for every point X in U, the section is an element of that system, so it defines what's called a germ, right? It defines a germ in that stalk at X, and take that point, and then take the set consisting of all these germs defined by that section, by that S, and make this, and this is a basis for the topology of the étale space. If you now let all of this vary, this is a basis for the topology. So now we really have a topological space. And it's clear what pi is. Pi, of course, just sends AX to X, little x, right, to the point X. So that defines pi. This is then a continuous map. And and this is very useful for the following reason. You can now define what a section is much more generally than in the pre-sheaf picture, because we can say, well, a section with respect to that étale space is just a map, a continuous map going backwards from X to A, such that this is the identity on X. This composition is the identity on X. In other words, that maps into the stalk over the point where you look at it. And so, therefore, you get groups of sections, which are usually written gamma of Y with respect to the sheaf A. But here, Y can be any subspace of X. It doesn't have to be open anymore. So you get sections over any set. So it's quite useful, right, to have this étale picture in mind. Okay, and let me also remark, if A is a sheaf, so this is a pre-sheaf, but if in fact it satisfies this condition G, if this is a sheaf, then if you take the étale space and take sections given like this into that space, it's exactly the same as the group that you started with. So that's the nice thing, right? So that's how these are related then. But be careful. if a pre-sheaf is not a sheaf and this condition is not satisfied, then you cannot make that assertion. And you cannot compute sections from the pre-sheaf groups like this. So one has to be very careful. You have to know exactly when this condition G is satisfied and when it isn't. Right? That's very important in this business. Okay, what else? Of course, it's clear we can speak of morphisms of sheaves. If now you have another sheaf, so these are both on the same space X, then you would say a morphism should be a continuous map between these spaces. It should also preserve stalks, so that you can speak about such restrictions to stalks. And all these restrictions should be homomorphisms. I mean, linear maps, right? In other words, linear maps of R vector spaces, right? For all X in X. So these are morphisms of sheaves, and this forms a nice category. In fact, you can also take the kernel of such morphisms, and that's a sheaf, and you can also look at the image of this, and that's also a sheaf. And so you get actually a very nice category, which I'll call sheaves on X, and it's not just a category with these morphisms, but it's in fact an abelian category, because you have kernels, images, co-kernels, and co-images, and the natural maps between those objects are isomorphisms, so that you have in fact an abelian, what's called an abelian category. So you can look at exact sequences of sheaves. All of these things that you're used to from groups, you can also do with sheaves, essentially, right? Is an abelian category. Now we need one more thing. What about maps between spaces? So suppose phi is a map from topological space X to another space Y. Now suppose I have a continuous map. Now there are two very important operations that are being used all the time. Namely, suppose you have a sheaf A on X. Then you can define a pre-sheaf on Y by saying if you have an open subset in Y, associate to it the sections over the pre-image of U under phi. And since phi is continuous, this is again open in X. And so you look at the sections that A has over that pre-image, and you assign this to U. And then since there are restrictions maps, this is a pre-sheaf, and it satisfies the condition G, and so is a sheaf. And it's of course a sheaf on Y, and it's called the push forward phi star of A. Now similarly, if you start with a sheaf on B, a sheaf B on Y, then you can pull it back. You can form a pullback phi upper star, written phi upper star of B. And this is a sheaf on X. And I don't have to write down how this goes, because you do exactly the same things as you do, for example, when you pull back vector bundles. Everybody knows how to pull back vector bundles. You write down exactly the same things. You get the pullback of a sheaf. Right? Okay, very good. So definition now. There are two concepts, two special classes of sheaves that play an important role in that theory. Namely, the so-called soft sheaves and the injective sheaves. So what is that? So A is called soft if for all closed subsets K of X, the following map is surjective. you consider sections over K. Remember, I'm now able to talk about sections over any subset. It doesn't have to be open. So this is well defined, right? And I look at global sections over X of A. Then there is the restriction map. And I want this map to be surjective. So in other words, if I can extend every section over a closed subset to a global section of the sheaf, then you call it solved. And I need another class. A is injective. If whenever you have a diagram as follows, so you have a monomorphism of sheaves and some morphism into I. I'm sorry, I should say I. Sheaf I is injective if whenever you have a diagram like this, you can find an extension to the sheaf B. So this is, in fact, exactly what you say in homological algebra when you define what an injective abelian group is, for example, or what an injective module is. So it's exactly the same thing. You always say this, right? So you have these injective objects. And these play an important role in computing cohomology, but I'll come to that in a second. So cohomology is something associated to complexes, so we need first to discuss, we need to say a few words about complexes of sheaves. So I leave single sheaves and I discuss complexes of sheaves. So I'll write them as A dot. This indicates the grading, and these are graded by Z. And so this is something like this. You have in every degree AI plus 1, you have a sheaf. And you have differentials, di minus 1, di, and so on, between these, such that d squared is 0, as usual, so that this forms a complex, right? So it's just the usual definition of a complex transported to the world of sheaves. So there's nothing special here. Now, such complexes, they have, now you have to be a little bit careful. They have various cohomology objects associated to them. One thing that you can do is you can associate a cohomology sheaf to this. And I'll write this as hi of A. And you can think of this in two ways. There are two ways to think of the cohomology sheaf. You can either think of it as the kernel sheaf of D modulo the image sheaf of the D below. But you can alternatively, so this is kind of a nice description because it's close to what we usually do. But of course, this is the same as, so you can also, if you have an open subset, you first form a pre-sheaf by assigning to U okay, so you take the sections over U of this complex. This is in its own right a complex, so it has a cohomology group that you can assign to it. And since you have restrictions, this forms a pre-sheaf, but unfortunately it does not satisfy condition G. This is not a sheaf, so you must sheafify it. You must run through all this étale space business and then look at sections, and then you can't use this formula anymore. So that's unfortunate, but there is no way around it. So you must sheafify it. You must sheafify this pre-sheaf, and then that's the same as this. So these are two ways to think about the cohomology sheaf. By the way, the stalks of this sheaf can be computed as follows. This we have to do all the time. We need to know at a point X what is the stalk of the cohomology sheaf. Well, because restriction to a point is exact, you can actually take it inside and say, first I look at the stalks of this complex at X, and then this is just a complex of real vector spaces, and I can take its cohomology and compute like this. It's the same thing. So this is how you compute stalks of cohomology sheaves of a complex. Now, what is an injective resolution? And this we need to define cohomology, global cohomology. Injective resolution is, so you start with a complex of sheaves. You do the following thing. You find a complex I dot, and this complex is injective, and this means that the individual constituent sheaves of that complex are injective in every degree. Injective for all I, the way I've defined it. And then you have a map from A to I, a morphism. It's of course clear, I don't have to write down what a morphism of complexes is, right? Because you just have morphisms in every degree, preserving degrees, and such that these maps commute with the Ds. That's of course a morphism of complexes, so I don't have to write that down. And so in that sense, you take a morphism from that complex to the complex I, and you would like this to be what's called a quasi-isomorphism. And what is this? Quasi-isomorphism. I'll often abbreviate this by QIS. And this means that on the cohomology sheaves, on all cohomology sheaves, this map induces an isomorphism. Okay? That's called often a quasi-isomorphism. So if you have a quasi-isomorphism to an injective complex of sheaves, you call that an injective resolution of A. And the fact is, these always exist. That's not too difficult. These are fairly standard arguments to show that you have such resolutions. And now with this, you can do the following. Now we define what's called hypercohomology, or sometimes just cohomology by people working in that area. Originally it was called hypercohomology. It's, I'll write it like this: HI, script HI of X with coefficients in a complex of sheaves A dot. So this is a generalization of sheaf cohomology. Usually you define the cohomology of X with coefficients in a single sheaf, but the word hyper refers to the fact that now you are defining the cohomology of X with coefficients in an entire complex of sheaves. That's why people say hyper, you know. But it's very simple. You just say, you first form an injective resolution, then you take global sections, and then you take the cohomology of that complex. And that's it. But this is a global object. This is not a sheaf. This is a real vector space. These are sheaves. So one always has to distinguish between these two. So there are various other operations we can do on a sheaf complex. Let me mention some of them let me mention those that we will need later.
Can you maybe comment a little bit why you need this step to pass to take first the injective resolution rather than just define it directly from A? Presumably this has some nice...
Well, because a general sheaf has way too few sections. Imagine it as follows. The constant real sheaf, suppose you plugged in for A the constant real sheaf on X. That's supposed to be the ordinary cohomology of X, of course. But so if you didn't do anything but just took the global sections of the constant sheaf, you would just get nothing, right? You would not get any higher cohomology groups. So you have to do something to soften it up, if you will. And so the way to do this, often in de Rham theory, is, so a good example is de Rham theory, is if you take the complex of differential forms, or the sheaf of differential forms, right, on a manifold, on a smooth manifold, then this is, in fact, a complex of soft sheaves, because this is satisfied, as one can show, right, for differential forms. And the fact is, in practice, oftentimes, if you have a complex and you know it to be soft, then you can use it directly to compute hypercohomology. Now, that's a theorem you have to prove, but it's true. Then you can compute the hypercohomology of such a complex by just directly taking global sections of these soft sheaves and then taking cohomology there. So an example is the de Rham complex. If you take, this consists of soft sheaves, and if you take global sections, then you just get forms, right? Then you get the complex of global differential forms on the manifold, and if you take the cohomology of that by de Rham's theorem, this computes the correct cohomology. So that's how you should imagine this. That's, I think, the best example one can give the de Rham resolution. But it's not, but in general, it's better, for the general development of the theory, it's better to look at injective resolutions rather than soft ones. But in practice, then, one often uses this fact that if it's soft, then it's already good enough to compute cohomology. And we'll use this later, in fact, also when we talk about intersection chain sheaves. So there are various other operations that one can do on complexes. For example, there's a shift that's important. I can, if I have a complex, I can shift it by n, by some integer n, and the ith sheaf in this is then simply ai plus n, and the differential in the shifted complex in degree I is by definition given by, well, it's in principle I plus n, the I plus nth differential in A, but there is a sign -1 to the n. So that's a shift, which we'll have to use. There is also the very important operation of truncation. And this is not surprising, because as we have seen, locally intersection homology truncates the homology of a cone. This we've proven in great detail, right, in this course. And so, therefore, the fact that you have to truncate certain complexes is not so surprising in light of our earlier findings. So how does this truncation work? So you fix a degree, and then there's a functor tau less than or equal k, which you can apply to a complex A dot, and it's defined like this. You have ak minus 1, ak minus 2, etc. with the differentials you had previously. But then when you're in degree k, you put the kernel of d in degree k. Here you still have dk minus 1. And then you continue on just with zeros. And so this gives you a new complex, and it's written like this. And the point is that the cohomology is cleanly truncated by this process. So when you do this, the cohomology sheaves of this new complex are given by the cohomology sheaves of the old complex when I is less than or equal k, obviously, and otherwise, if I is greater than k, it's simply 0. Right? So it cleanly truncates the cohomology. That's the value of this construction. Furthermore, you can, of course, define, if again you have a map phi of spaces, you can, of course, again define push forwards of an entire complex and pullbacks of an entire complex degree-wise. Define it degree-wise. So that's also no problem. Good. So that's what we need to know about complexes of sheaves. So now I go on to what's called constructibility. which is an important technical assumption that we have to make. So we will mainly be interested in sheaves that have the following properties. So I'll talk about constructibility and the so-called derived category. So what's all of that? Well, now I switch from arbitrary topological spaces to pseudomanifolds. Now let Xn be a topologically stratified pseudomanifold a complex A of sheaves on X is called constructible with respect to the stratification of X if the cohomology sheaves of A restricted to the pure strata, which are manifolds, right, are locally constant and finite dimensional. What I mean, maybe I should, more precisely, I should perhaps say, and have finite dimensional stalks everywhere, and have finite dimensional stalks, to be more precise. Then you call a complex constructible. Now, what's the derived category? I'll write it as d of x. This is the derived category of bounded constructible sheaves on this stratified space. So what exactly do we do? The objects are bounded complexes. So I don't want unbounded complexes, right? So I just focus on bounded complexes and constructible ones. So this will be now the assumption. These are the only objects that interest me. Bounded and constructible complexes A on X. But what are the morphisms? So I won't go into great detail here, but you should just remember the following thing. The only thing you really need to know about this is they are constructed in such a way that quasi-isomorphisms become isomorphisms in this category. So to discuss this precisely, one would have to introduce what's sometimes called roofs and so on. I mean, if you have a complex here and another complex B here, and you want to say what a morphism is from A to B, you actually define it to be a structure where there's a third object C, and there are morphisms of complexes both ways, and this one is a quasi-isomorphism. In fact, you look at this, the best way to look at it is in the homotopic category of complexes of sheaves, which I haven't introduced. So I don't want to go into any more detail here. There's a way of composing these. Actually, even more precisely, morphisms are equivalence classes of such structures and so on, but I don't have any time to go into all of these details. Actually, you don't really need to know it, because it never somehow enters explicitly into any argument, these kinds of things. You just need to know it to see how can I really make this into a category such that this is true, but later the only thing you use is that if you know you have a quasi-isomorphism and you are in this category, then in this category, this quasi-isomorphism will have an inverse, whereas it might not have as an inverse as a morphism of complexes. But here, all of a sudden, in the derived category, it will have an inverse, and that's extremely pleasant. That's a very good point of view for many things, actually. So this is the point of view we want to take here. So that's the derived. That's all one has to know about the derived category. And now we should say a word about derived functors. Now suppose you have an additive functor, say f, from some category of sheaves to some other category of sheaves, let's say. And suppose f is not exact, is not an exact functor, so it doesn't preserve exact sequences. Then you have the following problem. You would like it to induce, in a natural way, a functor between the derived categories of these spaces. But suppose you have a sheaf complex which is quasi-isomorphic to 0, and then to this morphism you apply f, and since f is an additive functor, this is just 0. So if this were, I mean, you would like this to be a quasi-isomorphism again, because if f should induce a functor on the derived category, if a functor always takes isomorphisms to isomorphisms. So if this is, after all, an isomorphism in the derived category, so if this would work, this should be an isomorphism as well. But then it should be a quasi-isomorphism, and this need not be true, because we said we took an f that's not exact, and it doesn't preserve exact sequences. So this would not be a quasi-isomorphism. So it doesn't take. So trying to induce a functor from f on the derived category is not directly possible, right? This is the problem one faces. And this necessitates the introduction of what's called derived functors. The point is you must first derive the functor, and then everything is okay. So how does that work? Okay, yeah, from that, okay, yes, right, in some sense, yeah. And so what we do is, again, these injective resolutions come into play, and we simply say, take an injective resolution. Actually, there's a canonical one. You can, in fact, make this canonical. Every sheaf complex has a canonical injective resolution, and then there isn't even a choice involved. So there's a way to make this completely canonical. I'm not going into it. And so injective resolution, and once you have it, you set RF of A. You define it to be F applied to the injective resolution rather than A. And the R stands for right, so I'm defining right-derived functors as opposed to left. Okay, so that's enough about that. So for example, if again you have a map phi from x to y, then we have a push-forward functor on sheaves. This is an additive functor, but it's not exact. And so we must derive it, and so you get a functor R phi star, right? And it goes from the derived category of x to the derived category of y. On the other hand, the pullback functor, this one here, is exact. I mean, not the whole, the functor. The functor is exact. The functor is exact. Therefore, by what we said, it's not necessary actually to derive it, and we don't have to write R phi upper star, but we just write phi upper star also. This is well defined on the derived category. So we have these things. So now we're almost done with the crash course on sheaf theory. But yes, question, yeah.
You need an assumption on your functor to be able to derive it. I don't think you can derive any functor like being left exact or something such that the right derivative exists.
Maybe, yeah, maybe.
Because a priori you
Yeah,
know if
yeah,
the functor
yeah,
represents
yeah, yeah,
quasi
yeah,
osmosis
yeah.
between injected
Yeah.
objects.
But the only things that are actually important for me is the push forward. That's actually the only, and global sections. So those are my main two applications. So yeah. So I need one last concept before we can then again talk about intersection homology. And this concept is the concept of Verdier duality. So this is a functor, the Verdier duality functor, I'll write it as script D, is a functor from defined on the derived category to itself. And it's characterized uniquely up to quasi-isomorphism by the following property. For all open sets, in X, the hypercohomology in degree I over U of the dual of a complex A can be computed as HOM, and then you look at hypercohomology in degree negative I with compact supports, so the C denotes compact supports, of U with coefficients in A. And you certainly know what that means. HOM into R. And so then if you know this, over all open sets, this characterizes this functor. And this tells you at the same time the only thing you need to know really to compute it. This formula we will then use to compute it. Now you can define various other concepts here. For example, if you take the constant sheaf R on X and you apply the Verdier duality functor to it, you get a certain complex called dx dot, and this is called the dualizing complex. So and in fact, you could go another route. You could define the dualizing complex first as the primitive object, and then define the dualizing functor, the Verdier duality functor, as R HOM, the right-derived functor of HOM, into not R, but into the dualizing complex. And then this would give you another way to define the dualizing functor. So that's how you can think of it. Yeah, and the stalk can be computed as the ith homology group of x rel x minus x. So you see, right, the stalk at a point x. So this is capital X, the dualizing complex on capital X, and that stalk, that cohomology stalk, can be computed like this. So these are the local homology groups of the space. So from this formula, you can see if X were a manifold, then by excision, this is like the homology of a ball rel boundary sphere. But since the ball is contractible, the long exact sequence of the pair shows you that this is isomorphic to the homology of the sphere with a degree shift. But you see, if the space were a manifold, this just looks like a constant system, like a constant sheaf, since we assume that everything is oriented. Actually, you should write down the orientation sheaf, but since we always assume, our standing assumption is that everything is oriented, therefore the orientation sheaf is the same as the constant sheaf. So then you would just get the constant sheaf with a shift. But if X actually is singular, then the neighborhood looks like a cone, not on a sphere, but on something else. And then these groups are not just in one degree, the homology of a sphere, but there can be complicated homology here in all sorts of degrees. And therefore, the stalk of this somehow measures how singular the space is. So it's a very appropriate object to look at on singular spaces, this dualizing complex. Although on a manifold, it's relatively uninteresting. But on a singular space, it's a very interesting complex of sheaves to look at. Furthermore, we can note things like d squared is the identity. I mean, well, let me just say it like this. D squared of A is isomorphic to A. This, by the way, things like that use the constructibility, because if we didn't require that the stalks are finitely generated, then you would have problems with this kind of biduality here. But so in various of these things, the constructibility already enters. Yeah. If you want to, yes, of course. So you can define it by this dualizing functor. As I said, you can define it as R hom into the dualizing complex, and that requires you to replace things by an injective resolution. Yes, so that's true. That's true. Okay, and then there are a couple of functors that you can actually define through dualizing. So yeah, so for X a manifold, as I said, the dualizing complex is canonically isomorphic in the derived category to the orientation sheaf on X with a shift by the dimension. But since we assume that everything is oriented, this is furthermore, so as X is oriented, this is furthermore isomorphic to the constant sheaf R on X with a shift. Now let's take again a continuous map phi from X to Y, and suppose that A is an object in the derived category on X. Then you can first dualize A on X. After having dualized it, you push it forward. But of course, you must use the derived functor of the push forward, as we discussed. Now you are on Y, and now you can dualize on Y. And you get a new functor. This functor is called R phi lower shriek of A. So there's also a shriek push forward by this formula. And similarly for the pullback, if you start with a sheaf complex B on Y, you can do a similar thing. You can dualize first. So you take B, you dualize first on Y. You pull back. I don't have to derive it because pullback is exact. Then I dualize on the other space, on X. And this is called, this also gets a name. It's correspondingly called phi upper shriek of B. So there's a, these are called push forward with proper supports or pull back with proper supports and so on. So these will also play an important role in intersection homology theory. So this is somewhat hard to understand what's really going on here. So let me give you another formula. How do you compute the stalks? We need these functors only in a very special case. Mostly we need to use those in the case where phi is J, the inclusion of a point in a space. So let Ux be a distinguished neighborhood of X in X. And so recall that this means, well, I don't need to say more. I mean, you know what that means. So it's Euclidean in the direction along the stratum, cross the cone on the link. And then you can compute as follows. If you have a complex A on X, and you apply Jx star, and then you want to know what the cohomology of this is, then this is the same as the hypercohomology of I, in degree I, over Ux with coefficients in A. I should say take a sufficiently small distinguished neighborhood, and then this is true. So you just take a neighborhood of that type, compute the, so that's the stalk, the cohomology stalk of a sheaf complex can be thought of that way. And now similarly, if you use the shriek restriction, you have a similar interpretation. So if I use, instead of Jx star, the ordinary restriction, if I use the shriek restriction and want to compute the cohomology of that complex over a point, then as it turns out, this is just the compactly supported cohomology of such a distinguished neighborhood with coefficients in A. So this is like a pullback with, you should think of this as a pullback with compact supports, right? This formula is very important for us, and we don't need much more about these functors. But all these functors make up a very powerful machinery of sheaf theory. These shriek functors, the Verdier functor, and the ordinary pullback and push forward functors. I mean, sheaves are very flexible. You can push them forward, you can pull them back, and so forth, and this makes a very powerful machinery. And next time I will apply all of this to studying the intersection chain complex. I will give an axiomatic description of that complex, and that will be seen to uniquely characterize the intersection chain sheaf in the derived category, and that's the main reason why we need the derived category at all. Otherwise, I wouldn't have had to introduce it. We will use that axiomatization then to prove the duality theorem. And then, if time permits, I would like to say more about width spaces and perhaps L classes. So that's the program for tomorrow. Thank you.